Hello everyone, welcome back. I'm your friend InsideXO. Today we will try to take a review at an old deep learning model, which is the sequence-to-sequence model. Why I have to do this? Because I think it is useful, especially when you hear about some news about the GPT-3, how amazing it is. So I decided to take a review at this model, and we will see how to use it with the Keras library. Okay, let's get started. First, let's read the introduction. This example demonstrates how to implement a basic character-level recurrent sequence-to-sequence model. We apply it to translating short English sentences into short French sentences, character by character. Note that it is fairly unusual to do character-level machine translation, as word-level models are more common in this domain. Of course, I know, but I think for this model, it is not only could be used at the translation software, it can also be used some one-to-one or seriously sequence-to-sequence model if you have such a data. Okay, for this algorithm, we will start with input sequences from a domain, for example, English sentences, and corresponding target sequences from another domain, for example, French sentences. And we will have an encoder LSTM turns input sequences to two state vectors. We keep the last LSTM state and discard the outputs. A decoder LSTM is trained to turn the target sequences into the same sequence but offset by one time step in the future. A training process called teacher forcing in this context. It uses as initial state as the state vectors from the encoder. Effectively, the decoder learns to generate a target time plus 1 by giving the target's time conditioned on the input sequence. In inference mode, when we want to decode unknown input sequences, like encode the input sequence into state vectors, start with the target sequence of ses1 or blah blah blah. I will just leave it there. Now let's just create an notebook. I think that would be useful. Okay, for this notebook, we will try to create a Python 3 script. And we will do something like, first we will import those necessary libraries. Okay, no error appeared here. Alright, let's go on. We will download the data. Let's just do it. Okay, you can see we got all those files that we need here. Then we make a configuration. For example, we say the page size equal to 64, the epochs equal to 100, the latent dimension equal to 256. The number of samples equal to 1 or 10,000. Number of samples to train on. The data path would be equal to the French.txt file. We can have a look at the FRA.txt file, and if you open it, you'll see something like this. At the first, it is the English sentence. Then after a table, it is the French sentence. Okay, now let's prepare the data. Normally we would have four variables: the input taxes, target taxes, and input characters, target characters. Okay, at the beginning we open that txt file. We get all those taxes and we split it by new line character. Then we say for each line in that line, we get the lines from that text. Then we split that line by the new tape by the tape character, so we can get the input text and the target text. Then for each target text, we add a tab character and a new line character. We add that text to our input texts last and target text last. And for each character in the input text, we add that character to our input characters set. And also we do the same thing with target text. So we can get all those individual characters in our dataset. Then we start to do some processing about those text. For example, for the characters, first we do our short, so it can have a static index. Then we get the length of of all those characters that we have, and we save it to the variable len encoder tokens. These are tokens. Then we use a method to get the max encoder sequence length, which in other way it is to get the longest text, how long that sentence will be. So basically what we do is get all those lengths from the input texts last. Then we use a max function to get the maxest value, or to get the biggest value. And then for visualizing, we print those parameters out. Then we started to give number indexed to the input token and target token. So for each individual characters at our dataset, they will have a unique index. Then somehow we just define the 3 NumPy array, and we limit encoder input data, decoder input data, decoder target data. Let's say how they define it. It uses in 0 as the initialized value, and the type of that value is float 32, and it's a 3-dimensional vector. The first dimension is input text, how many sentences we have. Then it is the max encoder sequence length, which is the longest sentence. How long the longest sentence we have. And in the end, it is the number of encoder tokens. So to be honest, this is a quite big vector, as we would say in the later. So the natural language processing is quite require computing resources. Then we do a zip for the input texts and target texts. So we want to zip it together and do some process about it. For each index, we do this. For T character in input text, we say the encoder input data, the I, which is indexed, then the T, which is another indexed, but for each sentence. Then you get the token indexed by giving it a character. So in this case, you can somehow represent all those texts at your dataset to pure number. And after that, you add a space out there to indicate that it is finished. Then for the target text, we almost did the same thing. But if the t greater than 0, which means that the t might be 1 or 2 or 3, we do something like this: decoder target data t minus 1, then the target character. To be honest, I really don't know why Hey, you want to do this? It is said that decoder target data will be ahead by 1 time state and will not include the start character. So this character won't be included. Weird. And after that, we say decoder input data t plus 1 equal to a space, and decoder target data t still equal to space. Okay, anyway, even if we still got a little bit confusing, we can still run this code, and it will work. It will tell you that the number of unique input tokens are 71. The number of unique output tokens are 92. The max sequence length for the input is 16. The max sequence length for the output is 59. Now we can, since we already have the data ready, we can just get started to build the model. So let's do this. First, we define an input sequence and process it. The encoder inputs would be equal to char input with a shape of num and the number of encoder tokens. Okay, that makes sense because we may not know the exact input length. So we set the first one to num. Then encoder equal to chars.layers.lstm. You know that LSTM means non-short-term memory. It's a layer dedicated for the natural language processing. Then it has how many elements it has, or how many nodes it has. It has the latent dimension. We defined it in here, so it got 256 nodes, or nodes if you prefer to say that. And it will return the state for sure. So we set the return state to true. Then we will get the encoder outputs stat h and stat c from the encoder function by giving the encoder inputs. So this is basically the process we have defined to do some process on the input data. Then we discard encoder outputs and only keep the states. So these outputs would be useless. We only keep the middle data, which is the state h and the state c, and we put it as a last to the encoder states variable. And we set up the decoder using the encoder states as initialized state, as initial state. So the decoder input would be equal to chars.input. Okay, it's a new model here. It's a new model. We say shape equal to num because we don't know the length of that. Then we say number decoder tokens. Okay, that makes sense. But to be honest, I think the number decoder tokens probably equal to the number encoder tokens, but I have no idea about that. No, it's not equal. They are different. Okay, we set up our decoder to return 4 output sequences and to return internal states as well. We don't use the return states in the training model, but we will use an in inferences model. It's another one, but here we focus on this. The decoder LSTM is a layer called LSTM. We gave it the dimension, which is 256. We say return sequence equal to true, return state also equal to true. Then the decoder outputs would be equal to decoder LSTM, which is this layer. And by giving it the decoder inputs, which is something that we get from here, and by giving the initial states encoder states. Okay, here it is the encoder states. So what it does, what the LSTM does here is to do a shape transfer. For example, the encoder states, it has a different shape. At least here, let's say it got 71. It got 71 elements in it, and this function, the LSTM function, will convert this stuff to the decoder inputs, which has Lambert decoding tokens, which has 92 tokens. So he did something like that. Then we add a dense layer here, and the activation function is softmax. We get the output by using the dense layer. Okay, finally we define our model. We say canvas.model equal to, we give it a list of inputs, which is the encoder inputs and the decoder inputs, and we get the result, decoder outputs. So to be more specific, the encoder input is the input, the decoder input is the target. Okay, now let's just run this code, and nothing wrong. We can go and train this model by using those code. We say model compile optimizer, which says the loss is a categorical cross entropy, and we do a fit by giving the encoder input data and decoder input data. Wait a minute, what is the decoder input data? Oh, we just define it. Then here we define the decoder input data here. Now if you take a serious look at this, you would say here we actually got two different variables. The first one, it is called the decoder input data. The second one, it is called the decoder target data. And the only difference between the two is that the decoder target data has a different time steps. It is the current time steps -1. Okay, let's read this sentence again. Decoder target data will be ahead by 1 time steps and will not include the start character. And when we define the model, we can easily understand what the encoder does is to take the encoder inputs. Here it is the encoder input data here. Then the second one, it is the decoder inputs. Decoder inputs, we define it in here. So the decoder inputs, it is also an input when we use this model. But the only difference is that it uses an initial state, which is called encoder states. So let's have a look at the decoder input data. Okay, here we go. So now, do you understand what's the difference between the encoder input data and the decoder input data? They were using two different sentences. The encoder input data uses input text. The decoder input data uses the target text. So they were using two different sentences. So here's the funny stuff. Even if I use the decoder input data from the target text, we wanna still use the initial state from the input data. So actually, what it does is, let's take a look at this. Is first we take the input text and we extract some features from the source sentence. Then we still use the target text. We use tokens on the target text, but we use the features that extracted from the input text and we use it to the target text. So in the end, we can get the right text that we want from the target text. So this is the basic logic about the sequence-to-sequence model. So this time I just really started to understand how this machinizing works. Before I just doing those things without any idea about behind the code. Anyway, let's start the training. it's not that quick, but as you can see, the accuracy is going up, which is a good thing, and the loss is going down, which is also a good thing. Okay, I just stopped this training because it seems like it will take a lot of time. So what we can do here is to change the epochs to, let's say, 3, so it can save us a lot of time. We don't have to get the finest result here because we only want to understand what's going on there. So I'll do a less training and just get to see the result. Okay, let's assume that we already finished the training and we can do a test somehow there. So for doing the test, we will have to run the following code. Before we run that code, let's read the text here. 1. Encode input and retrieve initial decoder state. 2. Run one step of decoder with this initial state and a start of sequence token as target. Output will be the next target token. 3. Repeat with the current target token and current states. Seems a little bit hard to understand, but we will go through it. Let's just copy this. Okay, finally we get a result accurate about 0.8. That's good.